Let's take a look at reactions between acids and bases. When I react an acid with a base, I get what's called a neutralization reaction. So this is the reaction of an acid with a base to produce a salt and water. So you should remember that hydrochloric acid is a strong acid and sodium hydroxide is a strong base. And when I react that acid and base together, not only do I produce some water, but I also end up with a salt. Sodium chloride in this case. And why is it a salt? Because it's comprised of sodium, which is a metal, and chloride, which is a nonmetal. Now we know that a strong acid like hydrochloric acid, when it's in that aqueous solution, so when it's in an aqueous solution, since it's strong, we defined a strong acid as an acid that completely dissociates into its ions. So we're going to break that acid up into its ions. So you see that we have the hydrogen ion or a proton, and then the chloride ion, and of course these are in an aqueous solution. And then we're going to do the same thing with our base because it's a strong base. And again, a strong base is going to dissociate completely into its ions. So let's see, we have the sodium cation and we have the hydroxide over here. Now, if we look at the products, water is a molecular compound, so it's not going to ionize. So we're just going to write water, still in the liquid phase. It doesn't break apart into ions. But sodium chloride, a salt, of course that's going to break apart into its ions. So we have the sodium cation and the chloride ion. We can call this equation an ionic equation because everything that can be broken apart into its ions has been broken apart into its ions. Now let's focus on the reaction arrow here and see what ions remain unchanged on both sides of the reaction arrow. Well, hopefully you can see that the sodium cation is the same on both sides, and so is the chloride on both sides. And if I just write down what's left over, so I have my hydrogen ion or my proton plus hydroxide, I get water. We call this a net ionic equation, which is shown right here. So the net ionic equation shows only the changed components, only the components that were actually involved in the reaction. Because if you think about the ions that were in solution from the acid and the base, the only ions that were reacting were the proton and the hydroxide. The sodium cation and the chloride ion, those remained completely unchanged. So what we do in this net ionic equation is we omit any ions appearing the same on both sides of the equation, and we call those spectator ions because they're just spectating. They're not participating in the reaction. By now you probably realize that a proton doesn't exist in aqueous solution. It's just H plus floating around. There's no such thing. There's a more correct way to represent that. H plus in aqueous solution actually exists as H3O plus, the hydronium ion. So this is a more correct way to represent the proton. And then if we go back to that net ionic neutralization reaction, a more accurate way to write that would be represented here. So instead of a proton, we have the hydronium and plus hydroxide. And look what we get as a product. We get 2 moles of water. But what's interesting is that this equation that I have shown here, this equation applies to any strong acid, strong base neutralization reaction. So any strong acid, it could be nitric acid, perchloric acid, sulfuric acid. Any strong base, it could be sodium hydroxide, lithium hydroxide, potassium hydroxide. The net ionic equation or the net ionic neutralization reaction is always going to be this reaction that's shown here. Now what we're going to see is we're going to be able to use a special analytical technique to determine the concentration of an acid or a base. And the name of that analytical technique is titration. It's important that all general chemistry students understand what a titration is. And a titration involves the addition of a measured amount of a standard solution to neutralize the second unknown solution. Now, if you're wondering what a standard solution is, the standard solution is a solution that we know the concentration of. And what we're going to see is that from the volumes of the two solutions and the concentrations of the standard solution, the concentration of the unknown solution can be determined. The way that you would conduct an acid-base titration is like this. You would take a known volume of that unknown acid, maybe let's say 25 milliliters of it, and you would measure it out very accurately and put it into an Erlenmeyer flask. So let's say you have 25.00 milliliters of HA, your unknown acid. Then you would put an indicator into the Erlenmeyer flask, and an indicator is a substance that changes color as the solution reaches a certain pH. Next, you would take your standard solution, which is in the buret here, and you would know the concentration of that standard solution. Let's say it's sodium hydroxide, and let's say it's maybe 0.1000 molar, just for interest's sake. And you would carefully add that standard solution to the unknown solution using a buret, which is a long glass tube calibrated in milliliters, which again contains that standard solution. Now it's hard to see here, but what I'm circling is a stopcock that's at the bottom of the buret, and it regulates the amount of standard that we dispense. The standard solution, we're going to keep adding it until the indicator changes color. At the point it changes color, or what we call the equivalence point, the number of moles of the hydroxide ion added is equal to the number of moles of the hydronium ion present in the unknown acid. And if we were adding a strong base like sodium hydroxide, and if this was a strong acid, then the pH would be neutral. It would be 7. So let's imagine we're doing the titration of hydrochloric acid with sodium hydroxide. I have the balanced equation written here at the top. Now what we're trying to do is figure out the concentration of HCl. So the concentration of HCl, we do not know what that is. What we do know is that we put exactly 25.00 milliliters of hydrochloric acid into this Erlenmeyer flask. Now in order to calculate the concentration of HCl, we're going to need the number of moles of HCl divided by the volume of HCl. Now again, we already have that volume, so what we need to determine is the number of moles of HCl. Now let's imagine that the concentration of our standard solution, our sodium hydroxide, is 0.100 molar, or I will write moles per liter. Now let's say it took 35 milliliters of sodium hydroxide to reach the equivalence point. We can use the concentration of sodium hydroxide and the volume of the sodium hydroxide to determine the number of moles of sodium hydroxide. So let's multiply the concentration by the volume. I'm going to convert this 35 milliliters into liters, so that's 0.03500 liters. And I determine that the number of moles of sodium hydroxide is equal to 0.003500 moles. Now again, in order to determine the concentration of HCl, I need the number of moles of hydrochloric acid. But if I look at my balanced equation, I can see that the ratio of hydrochloric acid to sodium hydroxide is 1:1. Therefore, the number of moles of sodium hydroxide is going to be equal to the number of moles of hydrochloric acid. And now I can calculate the concentration of HCl because I know the volume of my hydrochloric acid and I know the number of moles of my hydrochloric acid. So let's plug those numbers in. 0.003500 moles, I'm kind of running out of space here, divided by 0.02500 liters, and I get that the concentration of my hydrochloric acid is 0.1400 molar, or moles per liter. Since the pH at the end point of a titration can vary depending on the identity of the acid or the base, you would want to choose an indicator that has a detectable color change near the pH of the equivalence point of the titration. So let's say the pH at the end point of your titration was around 2. Well, in that case, thymol blue would be a good choice. Let's take a look at what makes phenolphtalein such a good indicator in the titration of a strong acid with a strong base. If I write out the net ionic equation for the titration of a strong acid with a strong base, and we looked at this earlier, when I reach the equivalence point, the number of moles of my hydronium is going to be equal to the number of moles of my hydroxide. Now, if the number of moles of each of those is equal to each other, all I'm going to have is water in my Erlenmeyer flask plus the salt, but that's not going to affect the pH, and I'm going to end up with a pH that's equal to 7. Now when I have a pH of 7 and phenolphthalein as my indicator, it's going to be colorless. When I reach the end point, that end point is reached by adding a slight excess of base. So I'm going to have a slight excess of my hydroxide. And what's that going to do? It's going to give me a pH greater than 7. And you don't have to add a great excess of sodium hydroxide. You only have to add a part of a drop. Even a tenth of a drop will do it to reach a pH of 8, which will be pink. You can see here that when I reach a pH of 8, I'm going to get a faint pink color. And again, the reason that phenolphthalein is such a great choice is because it's very easy for the human eye to detect a color change going from colorless to pink. You may be asking, could I use phenol red as an indicator? Yes, you could use phenol red, but it's much more difficult for the human eye to detect a color change going from yellow to red. To recap, the determination of the concentration of a solution of hydrochloric acid using titration, you would start by placing a known volume of your acid, in this case we're talking about hydrochloric acid, into an Erlenmeyer flask, and of course you don't know the concentration of that hydrochloric acid. That's the whole point of the titration. Then you would add an indicator, and we discussed why phenolphthalein is a good choice in the titration of a strong acid like hydrochloric acid with a strong base like sodium hydroxide. Now of course you know the concentration of that sodium hydroxide. You put that in the buret and you start dripping the sodium hydroxide into the flask until the indicator changes color. And as I talked about in the last slide, that when you're at the equivalence point, the concentration of hydronium is going to balance out the concentration of hydroxide. They're going to be equal. And at that point you have a pH of 7 where the solution would be colorless, like is shown here in A. So what happens when you reach the end point? You add just a tiny, tiny excess of your standard solution. And what that's going to do is phenolphthalein is going to turn pink. But the closer you get your end point to the equivalence point, the fainter pink it's going to be. So you are trying to get the indicator to turn the faintest pink possible. If your solution turns fuchsia, like this, that's not a good titration, because then you've added too much base. We call that overshooting the titration, or we say the titration has been overshot. And if you overshoot the titration, you can't assume that the number of moles of hydroxide is equal to the number of moles of hydronium. So if you end up with a solution that's hot pink like this, it might be better just to throw everything out and restart the titration. These pictures were taken from a video of somebody performing a titration. What I want to point out to you in the first photo is that it's one person doing the titration. Sometimes I'll come into the lab and I'll see one student swirling the Erlenmeyer flask and the other student operating the stopcock. Titration is a one-person operation. So not only do you operate the stopcock, but you swirl the Erlenmeyer flask at the same time. Also notice that the person put a piece of paper down here, and that enables you to detect the color change easily. Also, I told you that the end point is reached when you add only a slight, very slight excess of the stock solution. And I told you that you don't even have to add a whole drop. You can just add a tenth of a drop, and this will suffice to reach the end point. Now, you might be asking, well, how do I add a tenth of a drop? Well, what you do is you would open the stopcock so that you can see just a little bit of base coming out of the end, but it hasn't dripped out yet. Then you would take some deionized water in a wash bottle like this, and you would rinse it into the Erlenmeyer flask. So you can see that in the third picture, just to ensure that all of the sodium hydroxide coming from the buret has made its way into the Erlenmeyer flask, the scientist is rinsing the sides of the Erlenmeyer flask with some deionized water. Now, in the titration of hydrochloric acid with sodium hydroxide, the previous example, the acid and base combine in a 1-to-1 ratio. We saw that in our balanced equation. But not all acid-base pairs do this. So when we have what we call a polyprotic substance, it can donate or accept more than one proton per formula unit. Hydrochloric acid, HCl, is monoprotic because it produces one hydrogen ion for each unit of HCl. Let's think about that. If we break HCl up into its ions, we get a proton, one proton, and a chloride ion. Therefore, since we produce one proton, it's monoprotic. Sulfuric acid, H2SO4, which is a strong acid, when it dissociates, it's going to produce two hydrogen ions. If I write out a balanced equation for the neutralization of sulfuric acid with sodium hydroxide, I see that instead of a 1-to-1 ratio like I saw with hydrochloric acid and sodium hydroxide, now the ratio is 2-to-1. I need 2 moles of my sodium hydroxide to completely neutralize 1 mole of my sulfuric acid. The reason for this is that sodium hydroxide only has one hydroxide per sodium hydroxide, but sulfuric acid is diprotic. It has 2 protons, and thus I will need twice as much sodium hydroxide to neutralize 1 mole of my sulfuric acid. The dissociation of sulfuric acid to produce 2 protons is a 2-step process. In step 1, the sulfuric acid donates the first proton to water to produce hydrogen sulfate and the hydronium ion. In the second step, the hydrogen sulfate polyatomic ion donates its proton to water to produce the sulfate anion, SO42-, and hydronium. Now notice the reaction arrows in these 2 steps. In step 1, the sulfuric acid behaves as a strong acid. It's one of the strong acids that you should have memorized, and it's going to dissociate completely, and that's why we use the one-way arrow. In step 2, the hydrogen sulfate, which is not one of our strong acids, is going to behave as a weak acid. And that means it's only going to partially dissociate, and that's why we use the reversible arrows shown here. Now earlier on we saw that sodium hydroxide, NaOH, produces 1 hydroxide ion per formula unit. But barium hydroxide, the formula shown here, produces 2 hydroxide ions per formula unit. This also is a 2-step process. In the first step, the barium hydroxide will dissociate to lose the first equivalent of hydroxide, and in step 2, the remaining cation will dissociate to produce the second equivalent of hydroxide. The net result is that barium hydroxide will produce 2 hydroxide ions per formula unit.